for PageRank, right? Hi, everyone. Welcome back to part 4 of lecture 10. And now we're going to describe the PageRank algorithm, right? All right. So this is really the main application now, right? That is applied in the real world. With no Markov chains, well, we also apply it all the time. All right. So here's the setting, right? We have a directed graph that describes relationships between web pages, right? Like if a web page links to another web page, we put an arrow from the current web page to the ones that it links to. Okay. So, all right. Yeah, that's what we were saying, right? So there's a directed edge from I to J if page I links to page J. Now, what is the goal? We want an algorithm to rank how important a page is, right? And okay, so what is the intuition that we should have? Well, you know, if many other pages link to a particular page, then it must be that this linked page is really, really important because it's a reference page, right? That's a flagship of being a reference page. Oh, okay, like, look, you know. Okay, so this page is important. All right, so how do we capture this? So here's the PageRank algorithm. So what do? We get the web graph of all the web pages, and initially we just give each page the same rank because we don't know, we just know the relations, but we don't know yet like how many are there, right? Like, and the thing also is like, if you think about it, that's one intuition. Like if many other pages link to a particular page, then the linked page must be important. But also the other intuition that we should have, is what? Well, if an important page links to another page, this linked page must also be important. To a certain degree, right? Because if you have a reference that cites another reference, well, you know, it better be that the other reference is also of somewhat importance, right? So we need to give weight to this relationship. So what do? Well, all right. So initially we just say each page has the same rank value. And now what do? Well, in each step, right? And for each page, what do? We divide its page rank value equally into its outgoing link. So let's say if my value was 1 over n and I link 2 other pages, I'm going to divide my value. So I'm going to have 1 over 2n, and I'm going to send 1 over 2n of value to each of my like links, right? I'm saying, okay, here's my money. I'm giving you a little bit of my money, right? Like it's literally like they put your money where your mouth is, right? So all right, and then we're going to send these equal shares to the pages that I point to, right? So, all right. So now what do? So everyone does that in one round. So once we do that, we update the new page rank value to be the sum of the shares that I received. So I had 1 over n, that was my credit. I break it up, I send to people, I have credit 0, but other people are going to link to me, and then I get more credit and I keep linking. Does that make sense? Okay, great. So now let's do the example here. And just so that I make mistakes on these calculations. And again, so let's just do an example here. Like suppose that I have a page A, and this page A links to page B, and this page B links to page D, and A also links to a page C, and B links to a page E, and then D and E both link to a page H, and C links to the page F, and C links to the page G. And now what we have is that H is going to link to A, and G is going to link to A. Does that make sense? So this is, let's say, our web graph, right? So how would PageRank work? At first, I'm going to assign, I have 8 guys here, right? I have 8 pages. So I'm going to assign to each page 1 over 8, 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 1 over 8. Right? Now, what happens here, right? So what happens here is that, all right, so now if I do one step of this algorithm, what's going to happen? Well, what is the weight that A is, well, the first thing that we need to do is like A is going to divide its weight equally among its neighbors and send it to its neighbors, right? So what happens here? So A is sending to B. So B only receives weight from A, right? So A had a weight of 1 over 8 and it will be 1 over 16. Maybe let me put it in a different color. Like this will be 1 over 16. And C is also only receiving from A. So it would also be 1 over 16. Correct? Because I divided by 2 and sent to my neighbors. And then like B to D, right? So let's say B had D here and had E. Now, like D only receives weight from B, so we're also going to get 1 over 16. E is also going to get 1 over 16. And then now D and E, they both send information to, like send weight to H. So the weight for H here is going to be what? But D only sends weight to H, right? So I'm going to send all my weight, 1 over 8 plus 1 over 8, which is equal to 1 over 4. Correct? And now, if you think about it, and then H is sending weight to A, but we're going to get to A later. And then C sends weight to its two neighbors, which are F and G. And now F and G each will get 1 over 16. 1 over 16. And now, what are the other two? We know that G and H have to send their full weight. Oh, sorry, F also sends weight to A. Sorry, let me just put this because F cannot be just a sink. Well, it can, but it is not in my example. So, all right. So now what happens? We have that A is going to receive the weight, the full weight from F, which was 1 over 8 plus 1 over 8, the full weight from G, and it also received the full weight from H, right? So we have 1 over 8 plus 1 over 8 plus 1 over 8, which is 3/8. Does that make sense? And then this keeps going, right? So this keeps iterating. Does that make sense? Okay, and then, okay, we're gonna keep iterating this, but then you're like, okay, when do we stop? You may ask, right? And well, the thing is, well, now let's talk about what's going on PageRank, right? So this is the algorithm, and we saw how it works. Now, well, here's the thing. The equilibrium of PageRank, we just keep running it because what is the PageRank algorithm doing? The PageRank is essentially doing a Markov chain, right? So, but now the difference is you may ask, okay, an observation here is that, well, if I look at the PageRank, what happens is that my transition probabilities are changing, right? Because in the first, graph, my probabilities were A had 8, 1 over 8, and is sending 1 over 8 to like B and C. And in the second graph, I'm not sending the same weights. Right? So at every step, I'm multiplying like my vector of weights differently. Does that make sense? Because you can encode this, right? Like as we saw before, you can encode this as like you have the set of weights of all the vertices, and then these weights you're multiplying by a matrix P1. And then you get like, let's say you have weight 0, you multiply by the matrix P1 and you get a weight 1. Correct? And then here now, oh, sorry, no, this is fine actually, because all I'm doing like P is the same. Sorry, let's analyze this again, my bad. So what is P? P, I look at my outgoing neighbors, and my outgoing neighbors, they will never change. So the graph structure is not changing. So P depends only on the graph structure. sorry, I got confused with the homework on the graph structure. Correct? Because P is just like whatever my current vector is, I'm just going to look at my outgoing neighbors and I'm going to divide it evenly, which means P just depends on the graph, right? Like, for example, for A, it will be like, okay, from A, you take the weight of A and you multiply by half and give it to B, multiply by half and give it to C, whatever the weight is, right? So this gives us a Markov chain with the transition matrix P, right? Okay, so then we have that. So we know that the page rank is a Markov process. So page rank is a Markov chain. Now, once we know that the page rank is a Markov chain, we know that, oh, just run until it converges to the stationary distribution. Because the stationary distribution should be kind of the distribution when the ranks stabilize, right? Because no matter how much I refer, we're good. So now I stabilized, right? And then, and what is this kind of simulating? This is essentially simulating if we're all kind of randomly accessing, like if people in general were randomly accessing websites and we're just clicking like the random buttons anywhere, like what we're seeing is like, oh, which pages are we going to end up most looking at, right? Like, and those are somehow like the most important pages, right? Well, to a certain degree, I mean, you know, probably would end up in a page with cat pictures or something, but like, you know, so the thing is like, so we know that the page rank is a Markov chain. So then with the equilibrium of page rank values will be equal to the probabilities of the stationary distribution of this random walk. And here's the transition matrix that we were talking about, right? So the transition matrix is exactly characterized by this. Okay, so we have the transition matrix. It's very easy to compute because it just comes from the graph. We run this Markov chain until it converges, right? And well, but if you remember as well, like if we can also, if it's also easy to compute like the expected return time, then we also know what the stationary distribution is, right? So we don't need to keep doing this matrix multiplications all the time if we can guess like the return time, right? The expected return time. So, all right. So then this is what we discussed, right? Like, and again, if the web graph is finite, which, well, it is finite, right? Is irreducible and aperiodic, then we know that the fundamental theorem guarantees a stationary distribution, a unique one. But the problem is, well, in practice, this directed graph may not satisfy the fundamental theorem's condition, right? And why is that? Because, well, sometimes you have like disconnected components because, you know, like you can have like conspiracy theories, right? They are like kind of graphs that just kind of refer to themselves and they don't link to the real world, right? So, and then you have other things like, you know, you may have syncs, you may have websites that have no other links so that they don't link to anybody. So, all right. So how do we do to modify this graph? So what we do is we modify the original graph as follows, right? So we can fix a number like S between 0 and 1. And what we do is we divide an S fraction of its page rank values to our neighbors. So S is like the share that we're giving to the neighbors. And 1 minus S fraction of its page rank value goes to all the other nodes evenly. Right? Because that's one way of avoiding conspiracy theories, right? Because like the conspiracy theory will have to like give weight to somebody else. So if you're kind of in a closed loop, everyone is kind of losing rank to the rest, right? And it also avoids the syncs because if you have nobody, everyone will keep sending weight to you and you could be stuck on that point. But now everybody's sending a little bit of its weight for everybody, right? So, okay, so in particular, this resolves the main problem, right? Because essentially we're adding a complete graph like on top of the web graph, right? And once we do that, it's equivalent to the following random walk, right? Like with probability S, I go to one of my neighbors, uniformly at random. It's essentially if you're browsing web pages, like, oh, you know, like I'm browsing randomly, probability uniformly random, I go to my neighbors, but also there's some problem like, this website's boring, I go somewhere else. And then you just type a random address and you go there, right? So, all right. So now if you modify this, the resulting graph is strongly connected and aperiodic, which means that we'll get always a unique stationary distribution. But now we have to be careful, right? Like we have to set this parameter S so that things make sense, because if S is really close to 0, then it just means that we're kind of just randomly browsing, like we're not clicking any link, we're just browsing, you know, randomly, right? So what we want is to set this parameter S right so that, you know, we have a little bit of chance to go outside, right? All right, so then this modification, right? Another important thing to think about this is that this modification does not really change the relative importance of vertices, right? Because if a vertex is really important, even if all the vertices are going randomly to like a random other vertex, well, everyone else is doing the same. So the most important vertex will still remain more important, relatively speaking, right? So this S parameter is not something that will like mess up your rank, right? It's just something that will get your random walk to converge, but we know that whatever ranks you got, they will still be relatively the same. A more important page before is still more important than whatever other page you had, okay? So this modification is not something that destroys the property that you want to preserve, right? So, and this is really the full algorithm of PageRank. Does that make sense? So this is an application of like Markov chains in the super real world, right? And all right. So again, just to conclude these two lectures, what did we learn, right? So Markov chains and random walks are ubiquitous in randomized algorithms. You can use them. PageRank algorithm, for example, today's lecture. You can use them for approximation algorithms for counting problems. Another amazing final project. You can use them for sampling problems. You can use also for probability amplification without using too much randomness, and many more applications. Okay, and today, like the lecture was mainly based, like the first part of the lecture was mainly based on Hannah Karn's notes on Perron Frobenius. So you can see the link in the course webpage, and is in the lectures page in the references in the bottom. And you can also see Lapchi's notes, and also the book by Motwani and Raghavan, chapter 6. And yeah, you can see the notes there as well. Okay. So, and again, there's the same references if you're looking for final projects. Okay. So that's it for today.